Hello everyone, welcome to 6-4 Logarithmic Functions. Today we are going to learn to graph the transformations of logarithmic functions, and we're going to learn to find the inverses of logarithmic functions. Now we've transformed functions before, we've found the inverses of functions before, but we've never done it for logs, so we're going to do that today. Alright, first of all, let's talk about our parent function. So let's identify the key features of our log functions, so that way we know when we actually transform them, we'll know what we're coming from, right? So we're going to talk about the parent function today. So consider f of x equals 2x, and consider g of x equals log base 2 of x, right? So let's go and do that. So I went ahead and graphed. Our red graph here is our exponential function, and our blue graph is our logarithmic function, both with a base of 2. So let's go and just look at a couple points to start off with, right? So if we look at this point 0, 1, right, we notice that our y-intercept on our exponential function is at 1. We also notice our x-intercept on our logarithmic function is also 1, right? Now, I went ahead and plotted this line, y equals x, right? The reason why I plotted y equals x is because you can visually see that anything reflected over this line is also an inverse. That can be a really useful tool going forward, right? So if we use y equals x, we can find inverses more visually, and maybe that'll help you out a little bit. So if we want to determine if something's an inverse as well, mathematically, we flip the x and the y values, right? So if we go back to here, we're at 0, 1, our corresponding point is at 1, 0, right? These are inverses. If we go here, we have 1, 2, and then here we have 2, 1. So far so good. Let's just pick another point. This one works. We have 2, 4. So here at 4, 2, we should also, not first try. Oh, there it was. Yeah, 4, 2. Perfect, right? At 4, 2, we can see that these are still inverses. And if you pick any point, x comma y, on our 2 to the x graph, you pick the same point, y comma x, on our log base 2 of x graph, you're going to get the same thing, where they're going to be flipped, right? Okay, awesome. So that was just kind of me showing you in two different ways that we can show that the log is the inverse of the exponent graph. So let's look at a couple key features of just our log function here. Let's go ahead and get rid of this for now. All right, first of all, domain. Let's get rid of this too. You'll notice that for our domain, when we talk about just the x values, right, we never go negative, right? There's x's all over here, right, all on this side, but there's no x's over here. And the reason why is because when you start to get into exponential things, when you have negatives, first of all, you can deal with just things that don't exist, and then you can also deal with imaginary things, depending on what exactly is negative. But you'll notice here that it literally continues forever in the x direction, but ends at 0. So, as far as our domain goes, we are all positive real numbers. We can rewrite that as x is greater than 0, right? So that would be our domain of our base function here. Now for range, right, and maybe this would be useful to plop this back up here for a second, right? Because remember on our exponential function, our domain, it looks like the x values kind of end at some point, but they actually don't. They'll go forever, but it's just that because an exponential function grows so fast in terms of y, that it doesn't seem like it ever touches x, because y is growing so much faster than x is, right? Now, it's the exact opposite when it comes to a log function. Our x's are growing so much faster than our y values, but if we zoom out, we will eventually hit these higher y values, but it will be eventually, right? It's going to take a while. So the reason why I showed you that is to show you that while the domain of an exponential function is all real numbers, the range of a log-based function is also all real numbers. So our range, our y values can hit anything. It's just going to take a while, right? Our x-intercept is, as we just said, was at 1, right? And of course, we're using the x-intercept on this graph because it's the inverse of the exponential function. And then the other thing is the asymptote, which is at the line x equals 0. So it's a vertical asymptote that goes straight down here. And we'll talk about how we can move that a little bit here in a second, but we're just talking about the base function. So we have a vertical asymptote at the line x equals 0. All right, awesome. Now, I just wanted to show you real quick because we talked about e to the x, and we also talked about like the natural log in our last lesson. And I just wanted to show you that these are also inverses. We're just going to do this visually real quick. I'm not going to spend a lot of time on this, but if we replot our y equals x line here, remember that these should reflect over. So here's e to the x, and here's ln of x. Good enough. All right, let's just go and move on. Like I said, you can play around with that if you want to, but They are inverses. You can pick points, but let's go and jump into it. All right, so let's transform log functions. Now, if we transform a log function, right, we're going to have log base b times, and the x, so log base b to the x is our base, right? What we can do to it is, first of all, that b could change, right? We can multiply the whole function, the whole x value, by something, and that's what a would be. We can influence the number directly tied to the x, which is what our horizontal shift is here with h, and then we can just add any number at the end, and it'll just raise or lower the graph a little bit, just like k always does. Okay, so these are the things that we're doing to transform log base b of x, right? All these things are different things we can do to change it around. Now, just to kind of talk real quick, because it's always nice, because we already know how the exponential function works. So if we know how the exponential function works, we can kind of compare, and that'll help it kind of like drill into our brain a little bit better. So remember our initial function here for exponents is a times b to the x, where a kind of is kind of your y-intercept. It like will show you where the y-intercept is going to go, and then your b is like your scale. So the b and the a are usually the things that get confused. That's why I was kind of using this as an example, just to kind of show you the differences. But let's go ahead and look at a real quick, right? Because before, a was our y-intercept. With this graph, right, it's not our y-intercept, it's actually our x-intercept. So if we look down here, right, if we look at what we're doing here, right, so we have a equals 1, and our x-intercept is 1, right? Now, what's interesting is if we, I'm just, for the sake of this, I'm just going to pull this back up, right? You'll notice that in this case, we also have 1. And if we actually did the transformations before, like if you go back to the transformations from before, as a got up to 5, this would also increase to 5, right? So it was 1 to 1. If a was 7, then the y-intercept was also 7, right? Now, that's how it happens with that function. This function is the inverse, right? So the x-intercept isn't just equal to a, it's equal to the inverse of a, right? And this is actually really cool. It's really cool that you'll be able to see this. But let's go ahead and go down here, right? And well, let's get rid of this. And let's go down here. Now I'm going to make a 5, right? And remember before, if a was 5, then the y-intercept was 5. So let's do this. Let's turn a into 5 and watch what happens. Okay, well, it's obvious that our x-intercept isn't 5, because if we look over at 5, there's nothing. But what is it? It's 0.2, right? 0.2 is 1 over 5. So you'll notice that the x-intercept scales inversely instead of directly, right? Remember inverse variation, direct variation? This is inverse variation, right? And that makes sense. So we're literally varying it inversely to our exponential function. So as a increases, right, it increases at a rate of 1 over a. Our x-intercept does, right? So that's just kind of neat. I thought you guys would appreciate that. So now let's look at b. b is actually our base. This is going to do more than a does. A is just kind of affects the intercept point here. So let's look at b. Okay, well, a has to be 1. Okay, so let's look at b. Now, what we'll notice is as b gets bigger and bigger and bigger and bigger, this is actually going to stretch our x values, right? Our x values are getting bigger faster. In other words, it's not that anything is actually, it's like our y values aren't really getting smaller. Our x values are just getting bigger so much faster, right? So one way you could look at this is, let's go back to 2 and let's just pick a point and I can kind of show you, right? If we go back to 2, let's just pick this 1, right? Here at 1, we're at 1 comma 2, I think, if I remember. Yeah, 2 comma 1, right? So as y is 1, x is 2, okay? So we're going to look at this in terms of y equals 1. So if y equals 1 here, x is 2. Now let's make b huge. Let's make b 7. I don't know, it doesn't matter. Now, where does y equal 1 in this case? Well, if we keep going, right, here's y equals 1. It looks like it crosses like here, which is at 7, right? So we went from 2 to 7 by increasing b. So you see that the y value isn't really changing. The x value is getting much larger, much faster. So that's kind of what's happening here. Basically, it's stretching, but it's not stretching up, it's stretching to the right, right? Because that's what happens in this function. It's the opposite value that's stretching. Okay, so as b increases, x grows more quickly. Just kind of showed you that. Now, if b is greater than 1, we're going to grow. So let's go back all the way to like 1.1, right? And by grow, I mean, if we look at this graph, as x increases, y is also increasing, right? Like this is clearly going from negative infinity to positive infinity, right? Like this is the direction it's going. Now, what happens if b, well, first of all, b can't be negative, right? We've talked about that because our base can't be negative. That just, we won't have a function at that point, right? But what happens if we get just past 0, like 0.1? Did you notice how that flipped? Watch it flip, right? So when b equals 1, that's not even, this is basically a linear function at this point because, 1 to the infinity power is still just 1, right? So this isn't exponential at all. But let's go down a little bit, okay? So if we go to like 0.5, right, this would kind of be the opposite of 2. Let me pull up 2 just to show you. This is kind of neat, right? Do you see this? This reflects over the x-axis, right? So, in other words, if b is between 0 and 1, right? In other words, if it's like a fraction or a decimal, if b is between 0 and 1, it actually shows the equivalent of decay, right? So if we go back and get rid of this, right? This is actually exponential decay, but along the x-axis instead of the y-axis, right? Which doesn't really have as much utility in terms of like problems, but it's still nice to know that that's what that is, right? We do have like the inverse will also decay, right? All right, now let's talk about h. H is going to shift something that's very important in this case. Remember how y before would kind of raise or lower the asymptote of our exponential graph? Well, x is going to influence the asymptote of this graph. So let's go ahead and turn back b back into 2, just for the sake of having this here. Let's turn this back on. Okay, so here's our original graph. This is the one we were talking about. Now, watch what happens when we affect h. Remember, now you'll notice that I put x plus h here, but that's just so I can show you, like literally here, how it works. As h becomes positive, what happens? Well, it moves to the left. You can kind of see that, right? Let's go back to 0. Watch it move to the left. Boom, right? So at h equals 6, well, what are we approaching this time? We are approaching 6, right? So our asymptote moves based on our h value. If our h is positive, it moves to the left. If h is negative, it moves to the right. And that's the way it's always worked with transformations, right? Our h value goes the opposite direction we think it would. So let's put h back to 0. And now let's check out our y, right? So h we already know is the horizontal shift, which affects our asymptote. Positive shifts it to the left, negative shifts it to the right. K works the way it always does too. Positive is going to shift it up, negative is going to shift it down. So let's go ahead and just watch. Let's move this up here. Let's pick a point, okay? This is 1, 0, right? So if it's 1, 0, let's move it up 5. Just pick a point, 5, sure, why not? So now here, right, instead of it being, right, 1, 0, now we're at 1, 5. So we moved our y value up 5, right? And that's all it's ever going to do, right? It's just taking the function we have, and it's just moving it up and down. That's it. K is a warrior. He always does the same thing every time. You know what you're getting with K. All right, awesome. So those are the transformations you're going to see. Okay, if you play around with that graph a little bit, you can kind of get a feel for it yourself. But that was a good kind of basic rundown. All right, now let's talk about inverses. Okay, now we already talked about and proved for the most part that b of x and log base b of x, those are inverse functions. Right? B to the x and log base b of x, those are inverses. So let's go ahead and take a look at how we can find it, how we can find the equation of it, right? And now we're going to use logs that we learned in our last lesson. So find the equation of the inverse of f of x equals 10 to the x plus 1. All right. So first thing we're going to do is we're just going to rewrite the f of x as a y, right? Because we need to be able to flip x and y. So what we're going to do is we are going to replace this f of x with y, and now we have the exact same concept, right? Okay. Now we're going to flip the x and the y, and then we're going to resolve for y, right? So this is going to become x equals 10 to the y plus 1 power, right? And now remember, to undo an exponent, we have to write this in logarithmic form. So what we're saying is the base is 10, right? Which we learned as a common log. We don't even have to rewrite that. Right? So this is going to be log base 10 of x, right? Because x is our answer here. Log base 10 of x equals our exponent, which is y plus 1. Remember, a log is an exponent. So our exponent here was y plus 1. So now we are going to move the negative 1 over, right, because we want to get y by itself, and we will end up with y equals log x minus 1. So this here, y equals log x minus 1, is the inverse of x, or 10 to the quantity x plus 1. Kind of neat, right? Our x plus 1 becomes x minus 1, and our exponent becomes a log. Right? And our base stays the same, right? This is still base 10. So it's, I mean, everything is inversing, you know? So it's kind of cool. So we have our minus 1 instead of plus 1, and we have our log instead of our exponent. All right, let's do the same thing, right? Remember, turn our g of x into y, flip the x into y, solve back for y. That's how you find inverse, right? So let's try that for number 2, all right? G of x equals log base 7 of x plus 5. Okay, well this time, it looks like we have it in log form already, right? So let's flip our x and y, right? G of x, we're going to turn into a y. So y equals log base 7 of x plus 5. Now we're going to flip our x and y. So this is going to become x equals log base 7 of y plus 5. And now we're going to do what we did before, right? We started with a log. So shouldn't our inverse be an exponent, right? So if we started with a log and we're trying to turn it into an exponent, we need to think of what this means. Well, log base 7. So our base is going to be 7. And then our exponent is, our log is our exponent. So the answer here is x, right? So x is our exponent. So 7 to the x power equals, this is our, when I say answer, I mean this is our, this is what our equals will be, right? So 7 to the x equals our result, that's the word I was looking for, our result, which is y plus 5, right? And now, if we want to get y by itself, right? So we have 7 to the x equals y plus 5. To get y by itself, we're just going to subtract 5 from both sides. So now y equals 7 to the x minus 5. Now the minus 5 isn't in the exponent, just to be clear, it's just kind of off to the side here. But these are also inverses. And just for the sake of it, I went ahead and took this one, the 10 to the x plus 1, and the log x minus 1, and I graphed them, just so I could show you, right? So here's this one, and here's this one. And remember what we said before, if we use this y equals x line, we should be able to see a reflection. And I mean, just visually, if you're just using this to check your work, that's a good way of doing it, right? So this checks our work, this proves that we know what we're doing, and we're good to go. Awesome. So I would definitely practice these a little bit, right? This is more of a concept. This is more something you have to practice. And it's also just going to help you keep getting into that mindset of logs. I know logs can be tricky, especially when you approach them for the first time in a while, right? If you haven't done logs in a little bit and then you come back to it, it can be tricky. So come back to the logs, keep working on flipping between exponent and log form, and you'll get the hang of it. And these are actually, doing inverses is actually a really good way of making sure that you understand the difference on how to convert between the two forms. All right, so what did we do? We talked about transformations, right? We graphed the transformations of the log function, and then we also talked about using the inverses of b of x and log base b of x. All right, so that's it. That was 6.4. I'll see you in 6.5. Have a good day.